Thank you, Kusum. It's good to have a former student as the chair of the session. So let me begin by first mention of my collaborators in the two works I'm going to talk about. Abhijit Maite is my current PhD student. Aman is my former PhD student. Then we have Subir, who is here, and How You Go, who is a former student of Subir. This work wouldn't have taken shape in the present form without excellent, useful discussions with Subhro, Kedar, Yasser, and Darshan Joshi. So let's start with the very basics. So this talk is about thermal Hall response in gapped 2D systems, especially topological systems. Let's begin with something which we all have seen, which is the energy conservation in the form of a continuity equation. If I have some hydrodynamic picture in mind, and I make a gradient expansion of the energy current in gradients of either the energy density or equivalently the temperature, then the coefficient of the linear response is the thermal conductivity tensor. And its antisymmetric part, skew symmetric part, is what we call as the thermal Hall conductivity. As you can see, it doesn't contribute at all to this continuity equation. And moreover, it appears as a boundary contribution to the heat current. If you want to calculate the heat current through a cross section, let's say you have a strip and you draw a cross section in the vertical y direction. So the heat current passing through this cross section can be then seen as a difference of two quantities at the temperatures corresponding. These quantities are calculated at temperatures at the ends of this cross section. So that means maybe we should view this thermal Hall contributions as a boundary effect. And from a boundary perspective, there is a natural connection with the chiral central charge of the low energy 1D edge theory, because we like to think of 1D gapless physics as in terms of the CFTs often. And if that is the case, then the thermal current is known to be proportional to a quantity called the chiral central charge times the square of the temperature. And the constant of proportionality here is basically is a universal constant, and we will often interchangeably take KB and H cross equals to 1 whenever it's going to become cluttered. So if the difference between the endpoints of this cut are not very large, then you can simplify this a bit further. Here T is the average temperature and delta T is the temperature difference. So this gives us our thermal Hall conductivity as essentially the chiral central charge of the edge times the temperature. Now, as a bulk property, the chiral this also makes us wonder if the conductivity tensor here is a bulk property, because note that the chiral central charge is insensitive to details of the edge, since the thermal current must vanish in equilibrium. And the current, of course, is also insensitive to details of the temperature gradient. So from a bulk perspective, the desired properties of a microscopic bulk formula for the thermal Hall response must satisfy certain desirable things, like, for example, it should not depend on the details of the edge. And of course, it should correspond to what one measures experimentally. So the studies of thermal linear response goes back a very long way. It was Luttinger in 1964 who first used the method of gravitational potentials to obtain linear response formulae for thermal and thermoelectric quantities. So these are like this KXY Kubol I have written. Okay, but it turns out that if you really go and evaluate them, then it doesn't give the right answer. In fact, it almost invariably diverges in the thermodynamic limit. And so it was in 1997 that Cooper, Halperin, and Rusin pointed out that at least as far as certain quantities like the thermal Hall and also thermoelectric quantities like Nernst response are considered, the Kubo formula by itself is not adequate, and you need to subtract from these Kubo contributions a contribution which comes from the bound energy magnetization currents in the case of thermal Hall and bound magnetization currents in terms for Nernst. And so this quantity is essentially the uniform component of the energy magnetization, which is the energy analog of the current magnetization. So the notations that we will use are standard ones. So this is how the Kubo average looks like. Yeah. Okay, now that should have sorted the problem, and indeed lots of papers appeared which incorporated this energy magnetization subsequently. But in 2006, Kitaev, in his appendix of his enormous paper on the honeycomb Kitaev model, pointed out that the energy magnetization cannot be obtained as a unique function of the parameters, notably the temperature. And this makes the thermal Hall conductivity a very ill-defined quantity, at least theoretically. So what is it that the experimentalists are measuring? And the resolution was also provided by Kitaev and subsequently clarified in a very nice paper by Kapustin and his student. And in fact, I never understood Kitaev's original two-page explanation for all this, but then this big paper appeared, which everything is clear and it's tractable. So if you want to really read, then I suggest this paper is useful. So the resolution was provided by Kitaev, and he said that this thermal Hall conductivity is an ill-defined quantity, but the ratio of kappa by T happens to be an exact differential. That means that changes in kappa by T for different parameter values, these are well-defined quantities. In particular, if you take the parameter as the temperature itself, then the thermal Hall response satisfies a following differential equation, where every term here is now a unique function of the parameters. In particular, this quantity, which was born out of the energy magnetization contribution, it can be related to the temperature derivative of this ME. So now, although ME is not by itself a well-defined quantity, this tau E can be calculated very systematically. So since tau E since ME now needs to be obtained by integrating tau E at various temperatures, this means that this ME is only possible to know as a difference between two values at two different temperatures. Okay, so the theory was quite, the theory of thermal Hall response is, of course, quite non-trivial. However, the experimental situation, in my opinion, is not much better. So there are severe challenges of measuring thermal Hall conductivity reliably at low temperatures. And this is the poster child of the thermal Hall conductivity as a probe for discovering a non-abelian spin liquid, or sorry, non-abelian phase of matter. And this one is the nu equals to 5/2 quantum Hall state. So what these guys have done is they have plotted the thermal Hall conductivity coefficient K in terms of this universal constant as a function of temperature. So what they see is that if you are in this window of temperatures above 18 millikelvins to 26 millikelvins, this ratio is approximately 5/2, and this half odd integer thermal conductivity cannot be expected of an abelian state, and so the claim is that this is the first known discovery of confirmation of a non-abelian state. But unfortunately, if you go to lower temperatures, this coefficient goes on increasing, and that makes it a bit dicey, although the authors claim, and it's believable, that this rise is due to increasing equilibration length of the edge excitations, but then anything is possible, right? So we don't know whether it will go to 3 at sufficiently low temperatures, in which case the edge theory completely changes, makes it abelian. So this is the situation with the best case we have. And in the same year, in 2018, Matsuda's group made a very bold claim while making thermal Hall measurements with a Kitaev material, alpha ruthenium trichloride. And so the inset shows the temperature dependence over a big temperature range. But if you zoom into this low temperature value here, which is the main plot, you see that these authors find a sort of flattening at the half quantized value, which means that they might be looking at, so the claim is that you are looking at an Ising topological order, which is a non-abelian phase of matter. Okay, but this was immediately challenged by other groups. And so there is data here from the Fuanong group. And what you see is that this kappa by T plotted as a function of field at different values of temperatures. So if you go down in temperature, you find that the thermal Hall response in general monotonously decreases, and it is apparent that it will go to 0 if continued down to very low temperatures and not take a value which is some constant half. And there are plateaus also, but they are way below the half quantized value, and occasionally you see this overshooting as well. So these authors claim that there is no evidence for any Ising topological order phase. Instead, you can explain pretty much such behavior by just doing spin wave kind of analysis. So this makes us wonder if instead of looking at very low temperature behavior of the thermal Hall response, which is the best place, of course, but can we get something useful looking at finite temperature data? And this is what my talk is going to be about. So the first example of the two I want to give is one of an abelian chiral spin liquid in the Kagome system. We'll take a bulk approach here, and this is an analytic approach. So Subir and how you are involved in this work with us. So the model is very well known. It's the Heisenberg model on the Kagome lattice and antiferromagnet. And I add a 3-body interaction in addition, which is known as the scalar spin chirality interaction. Now, in the absence of this scalar spin chirality, the model has been extensively studied, and there are 2 schools of thought. One school believes that the ground state is a gapped Z2 spin liquid, and the other school believes that the ground state is a U1 Dirac spin liquid. And the weight of opinion has gradually shifted to the latter. And one of the early protagonists of this latter point of view, Yasser, is sitting in the audience. So we will accept this claim that the ground state is U1 Dirac spin liquid. If you turn on JChi or scalar spin chirality interaction, there things are much more not controversial. And it's known that this JChi beyond a certain small value stabilizes a chiral spin liquid. So you are invited to take a look at these 2 papers, for example. And it is also known that the chiral spin liquid shares the same topological class as the nu equals to half Laughlin state, which is described by a U1 level 2 Chern-Simons theory. So in other words, this is a state with semyon topological order. So with this accepted fact in mind, that the starting point is a U1 Dirac spin liquid, let's just Partonize the spins as usual and impose the necessary constraint of on the Parton number. we do a mean field decoupling of the
that adding even infinitesimal amount of chirality gaps will actually good.
so at the mean field level it does, but in numerics it's a small value, small non-zero value. Yasir is the expert. Yeah, that's right.
Yeah, just to understand the controversy, this cannot happen with the Z2 state. The gap states or any perturbations would be state. Why was there a controversy to begin?
I think if you numerically try to discover a gap, that's the problem, like a gaplessness.
Start from direct and the fermions. So I don't get.
But how do you explain the fact that you get the chiral trajectory?
Well, there are two different things. One is there, the other is different direct mass.
And it remains that U1 with this. So it becomes the U1 chiral.
Sorry, I didn't get your question. Yeah, but thanks. So, so in this mean field approximation, you ultimately end up with a tight binding model where the matrix elements of nearest neighbor hopping have phases. So in the Dirac spin liquid ansatz, the configuration of these phases is such that the energy is minimized if the hexagons don't have any flux, hexagons have pi flux and the triangles have zero flux. So this enlarges the unit cell to one of 6 atoms, and this is what I have drawn here. If you turn on J chi, then these thetas further change from whatever you had to do to get the Dirac spin liquid, and then it results in a non-zero flux phi through the triangles as well, and the energy is minimized for phi equals to pi by 2. So for such things you can look at, yeah. Okay, so here's the band structure of the spin-ons for phi equals to pi by 2. The distribution of Chern numbers is shown here. So it's -1, -1, 1, and then reverse. So if you add up the Chern numbers of all these 3 occupied bands, you get -1. And since there are 2 spin degenerate species, so total Chern number is -2, and that is what you expect for a semiotic topological order. Pi is the flux through the triangles. So that's in turn dictated by the phases you put on the nearest neighbor. Yeah, so now what we do is we can integrate out these lower occupied bands, which are called the heavy fermion bands, and leaving behind a theory that is described in terms of the light fermion bands. So here's the theory. I've gone to the continuum limit as well. Apart from these Dirac, massive Dirac kind of terms, you also get a Chern's U1 Chern-Simons term with level -4, which is coming from integrating out these 2 heavy fermion bands. And these gauge fields are coming from constraints you imposed for fixing the parton number. Okay. So just another point that in this Dirac theory, there are 4 fermion flavors because there are 2 Dirac points and there is spin degeneracy. Okay, so now recall what I showed you for the derivatives of the thermal Hall response. So what we do now is to just go and brute force evaluate it. The Kubo and the energy magnetization contributions turn out to depend only on the antisymmetric component of stress tensor correlators. And this method was first developed by Subhro's group in 2020. And so the quantity we are interested in is this T mu 0, T rho 0 kind of correlators. And both the Kubo and energy magnetization components follow from different limits of this correlator. Then the idea is to just calculate these correlators in some approximation scheme. Now there are no small parameters in the problem, so we have to make multiple copies of the model, that is NF, and then do some 1 over NF expansion for the stress tensor correlators. So the dominant order n diagrams contributing to the thermal Hall response are of this type. So solid lines represent the fermions, and these are the just vertices associated with the T mu news. This diagram also is there at order ON, but we showed that it identically vanishes. So this is out. So there's only one diagram at order N. At order 1, there are 3 familiar looking diagrams to many of you. These, if you have seen them in the context of superconductivity, go by the name of density of states corrections, Markey-Thompson corrections, a vertex correction essentially, and Aslamazov-Larkin corrections. Turns out that that for the thermal Hall conductivity, just like in superconductivity, everything is dominated by Aslamazov-Larkin. So these triangles that I have shown in dashed lines are in fact sum of 4 diagrams. So one of them is the triangle diagrams involving the fermion green functions, and to maintain gauge invariance and respect word identities, I have to add these also. So if we just go ahead and calculate the order n contribution, which is the free Dirac fermions from this diagram, you can actually get the full finite temperature profile of this thermal Hall response. For details, see this work. And here I want to draw your attention to 2 things. First, the intercept is 2. Which means the chiral central charge of 2 is being suggested from the free theory, which is not correct, of course, because we are looking at a semiotic topological order. And then at high temperatures, the thermal Hall response seems to saturate. So to now get the correct central charge of 1, which is that expected for semiotic order, we need to now consider the order 1 gauge contributions to the thermal Hall response. So one can look at it as 2 problems. One is low temperature regime, which has been understood for some time, and then the intermediate and higher temperature regimes, which is the point of this work. So if we look at the Aslamazov-Larkin contributions at low temperatures, it turns out that the internal structure of these triangles doesn't really matter. It is essentially a temperature independent vertex, and the whole thing then becomes identical to what you would have got by having a pure Maxwell-Chern-Simons description and doing gravitational anomaly like arguments to obtain the thermal Hall response of the Maxwell-Chern-Simons theory. So this is the result for a pure Maxwell-Chern-Simons theory. So here here there is no level. So here the level is -4, but for here the level will be -2. Which one? Yeah, this one. So it is there in this definition of the topological mass. Okay, so when I re-express it, I brought it back. Okay, so at low temperatures, if you combine the Aslamazov-Larkin corrections with the order n result, then you find that the Aslamazov-Larkin corrections eat into the free fermion contribution, and instead of 2, you get chiral central charge of 1. So this is the low temperature behavior. So when you raise the temperature, things become more challenging because the triangle vertices themselves become temperature dependent. This is because the fermions and bosons both have comparable masses. The bosons because of the presence of a Chern-Simons term, and the fermions because they are massive. So these masses are comparable. So both excitations begin to matter now, and this feature is absent in the pure gauge theory description that works at low temperatures. So the finite temperature results are the central contribution of this work. we have shown just a plot here. Details are found in the paper. So here, if you see at low temperatures, it doesn't make any difference whether you take the internal structure of these triangles into account or not, and you get the correct central charge of 1. But as you go to finite temperatures, then a discrepancy opens up between the two, as expected. And this difference is on account of a larger Aslamazov-Larkin correction from here, which grows logarithmically with temperature. So since the Aslamazov-Larkin contribution eats into the free fermion contribution, at some point this will catch up. And of course, the temperature at which when it catches up with the free theory is exponentially large, parametrically large in NF. So beyond which our large N theory is invalid, and you should expect a different behavior. But up till that point, we are kind of good with this large N analysis. So incidentally, this calculation was done by assuming essentially an infinite bandwidth for the Dirac fermions. But if you have a real system, the bandwidth is finite, you will be able to show, even for free fermions, that the thermal Hall response at high temperatures should go to 0 like 1 over T squared. And this is also a point which is made in the original work of Kapustin on very general grounds, that at very high temperatures, above any other energy scales in the problem, the thermal Hall response should go to 0 like 1 over T squared. And this is what we see. I am not showing that data. Okay, so next example, which I'll wind up in 2-3 minutes, is of a non-abelian phase that happens to exist in the isotropic Kitaev system on the honeycomb lattice. So we perturb it with a small magnetic field, and as many of you know, the presence of a small magnetic field in certain directions introduces a gap in the Majorana spectrum. And instead of having a Z2 topological order, the ground state has Ising topological order instead. So it is this state we are interested in. Now, for this work, which is an older work, we will take a boundary approach. So what we do is the following. So it's not a linear response calculation, which is very tough to do numerically. So what we do is we take a long strip of the material, and it has these two edges. We roll it up, make it compact in the short direction. Then we immerse this system in a uniform temperature bath. Incidentally, I want to just point out that this method will not work if I have gapless excitations, but we have checked it generally works if you have a bulk gap. So we immerse it in a uniform temperature bath and split the Hamiltonian into layers. So this dashed line shows a dual cut, and I want to calculate the thermal current that is flowing across the cut. So that is just given by the commutator of these two layer Hamiltonians. So this would, in principle, if evaluated with two different temperatures on these edges, would give you the thermal Hall current. But that's something we cannot do because that's a non-equilibrium situation. So what we do is we just immerse the system in a uniform temperature bath. And that, of course, means that the total Hall current is 0 because there is no temperature gradient. Nevertheless, things are not so bad because it's not because thermal Hall current is 0 everywhere locally, but it's because there is cancellations. If you look at the contributions from one edge and go towards the interior of the strip, you will find that the thermal Hall current gradually decreases, and if you are sufficiently far into the bulk, say 10, 12 lattice constants, it's generally very, very small. It depends on the size of the gap, of course. So because of that, what we can do is we can just sum up to the midpoint from one edge, and that would be our Hall current associated with that edge. And it would be exactly opposite for the other edge. To get the finite temperature results, we use a purification-based finite temperature tensor network technique. And these are the results, and this is my last slide. So So we can't go to very low temperatures or very large transverse dimensions of the strip because of numerical issues. So what we do is the following. So because of the finite transverse dimensions, the spectrum is not a continuum on the edge, but actually it is discrete. And this is the reason why you see decreasing thermal Hall conductivity, which is in fact size dependent. We have experimented with larger sizes and we find that this peak shifts to lower temperatures and also broadens. So we know that it's at least in the Kitaev regime, this is not a genuine peak followed by a dip. At the lowest temperatures that we could go to, we recover the half quantized thermal Hall response. And if you go on increasing the temperature, the thermal Hall conductivity falls very rapidly. If you turn on a magnetic field, then also the thermal Hall response more or less collapses after you cross the boundary that people know exists between the spin liquid phase and the trivially polarized paramagnetic phase. The behavior of the topological entanglement entropy, which we also track, shows more or less the same pattern. So this allows us to say that we have been able to calculate the chiral central charge of a non-abelian phase from microscopics without making any assumptions. And this is for a non-abelian phase, so I did not see any other such calculation of a non-abelian chiral central charge before. So that's the point we are making here. Um, if if I now look at the high field data, I can compare it with something and I can do analytically. So Darshan taught us how to do spin wave or topological magnons analysis of magnets at high fields. So we do the same and use the data for calculating thermal Hall. So you get these curves at different values of fields, and it actually agrees quite well with our numerical calculations. So this provides another consistency check on this crazy method, which produces the half quantization at low fields and the spin wave behavior at high fields reliably. Thank you very much.
Thanks, Vikram. We have time for a few questions.
Yeah. My understanding, may be incorrect, is that at least when there's a gap in the bulk, the thermal response Hall effect is always just at the edge. So is the temperature corrections and things due to at higher temperatures effect of the bulk, or?
So what we understood is that this this is definitely correct if you are at very low temperatures, but if your temperature exceeds that exceeds the bulk gap, then it is not true.
So
we are going beyond the bulk.
Above temperatures above the bulk gap.
Yes.
Thank you.
Any other questions?
The last very good motivation.
That's why I'm saying it's a bit of a cheating. So essentially we never go to large enough transverse dimensions that will get us away from the box quantization effects of these of these compact dimensions momenta. What we have seen is that if you raise the temperature a bit, provided that you are not very high and you are still within the Wison gap, then the thermal Hall conductivity peaks at half quantization and never goes really above it. And also, if we increase the transverse dimension, so this calculation was done with 3 hexagons, but if we can go up to 5 and not more than that, and we find that it shifts and also flattens. So that gives us some optimism that maybe it's like trying to flatten out, but this is the best we have got. Numerically, this should not be done. So yeah.
Right of the X,
The length,
the X channel that carries the X channel,
3 hexagons.
width of the channel.
Yeah, 3 unit cells. No, so size meaning.
You can correct the spread over a few lattices.
Oh, how deep does it go to? I mentioned that it goes up to typically for these parameter values about 10 odd unit cells, after which it is really small.
Yeah. So
But we try to do the same calculations for the gapless bulk, and it gives bullshit. Yeah.
Vikram, one last.
Sorry.
So most of the real materials have non-cative interactions as well. So is this plateau supposed to survive when there are other interactions?
So if the ground state does not have Ising topological order, no, you won't get half quantization. And I actually wanted to criticize the
So are you
Madhava paper more.
Yeah.
Yeah. So point is that, there are various things you can point out which makes it highly unlikely like what the story is. For example, if you take the pure Kitai model, ferromagnetic interactions, ferromagnetic Kitai, which is what the material is about, then it is extremely fragile. So if you put a magnetic field which is like 2.5% or less in the 1-1-1 direction, it already destroys the topological order. So here they have a substantial magnetic order, which is like 10% of the Kitai interactions. So to kill that, they put a magnetic field which is comparable, which is like 10% of the Kitai interaction. That has really annihilated any topological order you would have got, even if you say that, okay, once I kill the topological order, once I kill the magnetic order, there's a revival of the Ising topological order. That could have happened had I still been inside the window where the field was still small and wouldn't have killed the topological order in the Kitai model, but it's long dead. So I don't know what they have. Yeah.
Thanks.
Any other questions? If not, let's thank Vikram again.
Thank you.